In this video, I want to look a little bit about some energy changes that occur during a nuclear reaction. And specifically, we're going to look at binding energy, which really isn't involving a nuclear reaction, but does include nuclear chemistry. So essentially, binding energy is the energy that holds our nucleons. Remember, nucleons was the particles in our nucleus, so protons plus neutrons, together in our nucleus. So essentially, the mass of the nucleus, let's actually say the mass of the nucleons in the nucleus, which is kind of redundant because nucleons belong in the nucleus, but I think this will make more sense. So the mass of the nucleons in the nucleus is actually different than the mass of the nucleons when isolated. So the mass of the nucleons in a nucleus is different than the mass of the nucleons when isolated. So if we were to look at carbon-13, for example, right? Carbon-13 has 13 nucleons, 13 particles in the nucleus. And if you were to take the mass of a proton and multiply it by 6, because there's 6 protons, the mass of a neutron, multiply it by 7, because there's 7 neutrons, add that mass together, that number that we get is actually different than the mass of the nucleus itself. We get that by taking our isotopic mass and subtracting the mass of our electrons from it. So essentially there's a mass defect, right? We're losing mass when we put them together in a nucleus. That missing mass is actually going to be converted to energy. That energy is going to be called our binding energy. So there's a mass difference when in the nucleus. So our mass defect right? This is the loss of mass that occurs when protons and neutrons combine to form a nucleus. This missing mass, our mass defect, is actually then converted to energy. And this energy is called our binding energy. And that's essentially the energy that holds our nucleons together in our nucleus. So essentially, we're not obeying the law of mass conservation. We're not obeying the mass of energy conservation. We're obeying those two laws together, right? Mass itself is not conserved because when we form the nucleus, we're losing mass, and then we're getting energy out of it. So what we're doing is we're observing the law of mass, energy, and conservation together, right? They're not being conserved separately, but we're interconverting mass and energy, and then the combination of the two is conserved. So our laws of mass and energy conservation are conserved together, or observed together. Right? Our mass is converted to energy and the combination is conserved. So mass and energy are interconverted and the combination is conserved. So we're going to go through an example where we calculate the binding energy of an atom. And as usual, I think that the easiest way is to just actually go through the example and then I'll explain it as we go through. So we're going to do a binding energy calculation. Generally, binding energy is going to be expressed as electron volts per nucleon. And actually for us, it's going to be mega electron volts per nucleon. Remember, mega is 10 to the 6 of anything. This actually doesn't look like nucleon. I just want to rewrite it so my writing's at least half legible. Remember, joules is generally our SI unit for energy, and it still is. It's just that binding energy is usually not expressed in joules. We do need a conversion between electron volts and joules. So 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. We also need the mass of a neutron, proton, and an electron. So we're going to write that down here also. So the mass of a neutron is 1.00866 atomic mass units. The mass of a proton is 1.00728 atomic mass units, right? We've always said that the mass of a neutron and the mass of a proton are very similar, right? They're not exact, as we can see, right? These numbers are different, but they are very similar. If we were to round them to 3 significant digits, they'd both round to 1.01. We are going to carry out quite a few digits after our decimal point in this calculation, so do be careful to not lose digits. All of our numbers are going to become quite long. And then the mass of an electron, we always have said that the mass of the electron is much, much smaller than that of a proton or a neutron, and it is. I have 5.486 times 10 to the negative 4th atomic mass units. So the example that we're going to do is we're going to calculate the binding energy and we're going to do it in mega electron volts per nucleon for iridium 174. And our isotopic mass of iridium 174 is 1.73.9666, 4 sixes atomic mass units. So we can already see that mass defect, right? If we were to look here, I have 174 nucleons, right? I have 174 particles in my nucleus. And even if we were to round these, 1.01, right, for both of them. So 174 multiplied by 1.01 plus the mass of my electrons is going to be a number larger than 174. But if we look at the actual mass of that isotope, it's actually less than 174, right? We're already seeing that mass defect. These numbers are greater than 1, so we expect, right, if we have 174 particles and we do the math, it should come out to greater than 174. But this is less, so that mass defect. So our steps. First step is we're going to calculate the mass of the nucleus. And you can or the mass of the nucleons. You could do those in either order. They both have to be calculated separately. So let's do the nucleons since we were just talking about that. So first, sorry if I'm being confusing already. First, calculate the mass of the nucleons. So essentially we're going to look at how many protons we have, how many neutrons we have, multiply them by their corresponding mass and add it together. So I do need my atomic number. So find IR in the periodic table. It has an atomic number of 77. So I have 77 protons, and then 174 minus 77 gives me 97 neutrons. So I'm going to take 77 and multiply it by the mass of a proton, 1.00728 atomic mass units. I'm going to take 97, multiply it by the mass of my neutron, 1.00866 atomic mass units. So grabbing my calculator to do this math. Again, we're going to be carrying out a lot of digits, so just be really careful when you're typing these into the calculator to not miss something. Usually we round to 2 or 3 digits after the decimal point. So for this one, I have 77.5606. So significant digits, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then atomic mass units. And now I'm doing my neutrons, so 97 times 1.00866. And I get 97.8400. Again, significant digits, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we're just going to add those two numbers together. And I get 175.4006 atomic mass units. And then when we're adding, it's digits after the decimal point. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So even though I now have more significant digits, my rule for adding, remember, is digits after the decimal point. So this is the mass of my nucleons when they're outside of the nucleus. And again, we can already see that it's much larger than this number. And this number here includes my electrons. So that's going to be our next step, is we're going to actually calculate the mass of our nucleus, right? This is the mass of my atom. I need the mass of the nucleus. So next step, calculate the mass of the nucleus. Right? What we need to do is we need to subtract the electron mass. Remember, we've always said that electrons were pretty light, right? Often they're considered negligible. Here, we're not going to consider them negligible. We are going to acknowledge that the electrons do have mass, and we're going to subtract that mass from the mass of our atom to get the mass of our nucleus. So if this is uncharged, and we're going to assume it's uncharged unless we're told otherwise. So I don't have, a plus or a minus or anything written on here. So because it's uncharged, my number of negative charges are going to equal my number of positive charges. So because I have 77 protons, I'm also going to have 77 electrons. So I'm going to take 77, I'm going to multiply it by the mass of my electrons. So going back up to our list here, 5.486 times 10 to the negative 4. Atomic mass units again. And then I'm going to grab my calculator and do that math. And I got 0.04224. Again, watch significant digits, 1, 2, 3, 4 significant digits. These leading zeros don't count, so 1, 2, 3, 4 significant digits. And then I'm going to subtract now my mass of my electrons from the mass of my atom. So the mass of my atom is up here somewhere, and I'm just going to copy it because if I scroll back down, I'll probably misremember it and then have to scroll back up. So this is the easiest way for me. So that's the mass of my atom. I'm going to subtract from that the mass of my electrons. And then that's going to give me the mass of my nucleus. So 173.9, and then 4 6s. And I get 173.92442. Watch. So we're subtracting that, so it's digits after the decimal point. So here I have 1, 2, 3, 4, 5 digits. The 0 does count as a digit, so 1, 2, 3, 4, 5 digits. I want 1, 2, 3, 4, 5 digits after my decimal point. So this number here is the mass of my nucleus. And again, we can see that that mass is different, right? I'm not conserving mass here. All we're doing is we're taking our nucleons and we're forming a nucleus out of it, and we're losing mass. So our next step is, what is that mass? So we're going to calculate our mass defect. Meaning we're just going to subtract those numbers. So the mass of my nucleons, 175.4006 atomic mass units, minus 173.92442 atomic mass units. So grabbing my calculator again. Again, just be careful. There's a lot of numbers here, so make sure when you type them in, you don't rush it. And I get a minus, oops, not minus, I get 1.4762 atomic mass units. So again, I'm subtracting, so digits after the decimal point rule, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4. So right number of significant digits. So this here is my mass defect. That's the amount of mass we lost when our nucleons formed a nucleus. That's the mass that's then going to be converted to energy. So that's our next step. So convert to energy. And the equation that we're going to use to do that, or our formula, is probably the most famous of all science formulas out there. And that our change in energy, right, is going to be equal to our change in mass multiplied by the speed of light squared. So E equals mc squared, right? That's converting mass to energy, right? We're saying that mass is equal to energy. C is the speed of light, it's a constant. So if we take mass, multiply it by a constant, we're going to get energy out of it. And of course, we're looking at the change. So we do know that the speed of light, C, is equal to 2.998 times 10 to the 8th meters per second. And that would be given. You don't need to memorize the speed of light. And then we also need just a couple conversions here. I know that 1 joule is equal to a kilogram per meter, meter squared goes on the top, kilogram meter squared per second squared. because we are going to come out in units of joules here, and then we will convert from joules to our electron volts per nucleon in our next step. But right now we're just going to solve in joules. So the other piece of information, I guess, is we do know back from our intro chem days, right, that numerically something in atomic mass units is the same as in grams per mole, right? If we talk about the atomic mass of carbon, it's 12.01 atomic mass units. If we talk about the molar mass of carbon, it's 12.01 grams per mole. So I am just going to take my mass defect here in atomic mass units and change those units to grams per mole. Once I do that, we can convert to kilograms. Once I multiply by the speed of light squared, that's where this part is going to come from. So essentially what we need to do is we need to take this number, convert it to kilograms per mole. When I multiply it by the speed of light squared, then I will end up with joules per mole as my unit. So let's actually write a couple of those notes down. So we need to convert, we need our mass defect in kilograms per mole. So let's do that step first. So I have 1.4762 atomic mass units, which is equal to 1.4762 grams per mole. And then we know that there is, right, 10 to the third grams in a kilogram. So if we convert this to kilograms, I get 1.4762 times 10 to the negative third kilograms per mole. So that's the value that we're going to plug in for mass here. Right, that's my change in mass, right? We subtracted, we got our change. We are just assuming that atomic mass units in grams per mole, right, are directly proportional to each other, and then converted from grams per mole to kilograms per mole. Okay, so plugging these into my equation, I have that my energy change is going to be equal to 1.4762 times 10 to the negative third kilograms per mole multiplied by my speed of light squared. And then we'll grab our calculator here. And I got 1.3, where are we for significant digits here? We're at 4 of them, 1.327 times 10 to the 14th, and then just looking at units, I have kilograms meters squared per mole second squared, and this part here, right, is joules. We go back up, that is joules. So just rewriting it one more time, 1.327 times 10 to the 14th joules per mole, which is a huge number. Remember we had said that our energy changes for nuclear reactions are much larger than our energy changes for chemical reactions. So even if we converted that to kilojoules, right, it's 1.327 times 10 to the 11th kilojoules per mole. We're used to seeing things like in, you know, the tenths place, like 97 or maybe 130 kilojoules per mole. This is a huge number when we're dealing with energy compared to what we're used to in chemical reactions. So at this point, we really have binding energy. I have the energy in terms of joules per mole. The next step is just unit conversions. If you were doing a problem that didn't specify units, but didn't say milli-electron volts per nucleon, you could actually leave it this way. Since we specified units, we need to do a unit conversion. But again, at this point, we have converted to energy. Right? This is the energy that's holding those nucleons together in that nucleus. So our last step is we're going to convert to mega electron volts per nucleon. Right now we have per mole, we want per nucleon. So we do need, we'll just write it down here again. We know that 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. So we're just going to do straight dimensional analysis here. So I'm going to start out with my given. So that's the number we just calculated. And this is going to be kind of long, so I'm going to start over here. And I'm not going to write super huge. Otherwise, we'll run out of room. So we need to convert joules to mega electron volts. We also need to convert moles to nucleons. You can do whichever one you want first. I'm going to convert the moles first. So I have moles on the bottom. I know using Avogadro's number, right, that's the number of particles in a mole, that I'm going to have 6.022 times 10 to the 23rd nuclei per mole. And then looking at, if we scroll back up, this nucleus, I have 174 nucleons per nucleus. So we're going to go from moles to the number of nuclei that we have, and then from the number of nuclei to the number of nucleons, right? Remember, nucleons are the number of particles in my nucleus. So it's going to be a two-step process. Because I have moles on the bottom, moles are going to have to go on top, which means Avogadro's number is going to go on the bottom. So 6.022 times 10 to the 23rd, anything, right? In this case, nuclei per mole. And then moles are going to cancel out. Now that I have nuclei on the bottom, nuclei are going to go on the top. So I know I have 174 nucleons per nucleus, right? The singular of nuclei. So those are going to cancel. So I've now done the mole to nucleon conversion, right? I want nucleons on the bottom. I have nucleons on the bottom, so we're done with that part. I'm now going to use this to convert from joules to electron volts, because joules are on the top, joules have to go on the bottom. So 1.60 times 10 to the negative 19th joules per electron volt. And let's actually get this one, and then we'll convert to mega electron volts in our last step. So I'm going to grab my calculator and work this one out. Again, there's a lot of digits, everything's in scientific notation, so make sure you're using your calculator correctly when you're typing it in. It's taking me a minute here, sorry. Hopefully you're typing along at the same time. And I have a big number here. I'm just going to write down all, not the whole thing, but I'm going to write down all of it before the decimal point here. I guess 8.3 this would round up to. Actually, I'm going to type that in one more time. Sorry, guys. I did this problem on paper before I started the video, and I actually got a different answer. So let me do it one more time here. Since I don't have you to check my work. Yeah, I got the same thing this time. So we're going to go with it. 79,151,5,183. And then right now my units are, right, these joules canceled. So my units right now are electron volts per nucleon. And then we're going to convert to mega. I know that there's, right, 1 electron, we should say 1 mega electron volts is equal to 10 to the 6 electron volts. So I'm going to essentially just move my decimal place over those 6 places. So 1, 2, 3, 4, 5, 6. You could divide it by 10 to the 6 by a million. Same sort of idea. I do only want 3 significant digits at this point. Here I have 4. Here I have 4. Exact number because it's a counting number. But I have 3 here also. So I'm going to go with 3 significant digits. So this is going to be 7.92 mega electron volts per nucleon. And again, that then is the energy that's holding it together. Higher binding energy generally does correspond to higher stability, right? It's more stable if it has more energy holding it together.